My name's Andy Walton. I work in our System Solutions Engineering Group in High Wycombe. We work with our customers and on larger designs for our FPGAs, help people get the best use of them, and also to help Altera understand how our FPGAs are used in large designs. We don't design the FPGAs themselves. Those are SoCs basically, and have standard SoC start verification challenges. So when Mike contacted us and asked us to do this, he seemed particularly interested in FPGA challenges. So I got a group of people together to discuss this, and we tried to find some verification challenges more specific to FPGAs. We have all the standard ones that SoCs have as well. Also, we have a variety of design styles. For example, we can take some DSP specifications and generate RTL from those, which we use, and we didn't really want to focus on those verification challenges. For this audience, it seemed more appropriate to be focusing on more traditional RTL designs. And we get those because we use our designs. Within the FPGA community, I think there's a tendency to do reuse by editor as much as by parameterization. That means that the designs may make relatively small changes which can have a larger effect on the test benches. We use standard IP, and sometimes we have IP from third parties or our customers. So the first challenge we agreed on was our unique selling point, the flexibility. FPGAs can be viewed in many ways as software. You can change them in the field, you can ship them, ship upgrades, and you can use them to experiment. You can explore your design space when you're developing a product. This leads to a more software-like agile approach. And also you can play games. You can say, okay, we can release with this level of functionality and add functionality, something you could never do with an SoC. And the consequence of this is there's a lower verification bar, at least for initial deployment. Now, this doesn't mean that people ship FPGA designs that aren't verified well. One of our customers told me recently that when they release their product, it takes them to get a year to get qualified in their customer base. So once that ships, it has to be right. But the development process can exploit the fact the FPGA doesn't have to be completed in one go. However, there's still hardware. You still have to close timing. It has to fit on the FPGA. So what we found is that a waterfall style approach doesn't work. Stopping and having this what's sometimes called manager worry time, where you build this really complicated verification environment, tends to have a problem that by the time you've done it, things have changed. So you're extending this time, and you're not doing much testing because you keep working on this complicated environment. And then manager worry becomes manager panic time. So our challenge was to find some more agile approach to the verification where we can incrementally improve the verification environment and not have such a large amount of effort developing these complicated test benches. The second challenge we have is obviously UVM and its brethren are relatively new. There are lots of test benches around for existing products. As I say, people have had things for a while. They edit the IP. They may have some rough test bench that goes with it. And we get things from customers as well. In most cases, we don't have a UVM environment. So we need to try and, if we have a system where we have some UVM and some non-UVM components, and we're trying to test these in a UVM environment, we need to accommodate the lower level blocks. And sometimes this can have a dramatic effect on the IP. For example, in some of our designs we have policers that remove packets, so we feed a packet in the whole system and something in the middle takes it out. We need to configure this. We need the behavior of that to be reflected in the overall system scoreboards. So we need to solve this problem of interworking between legacy and UVM world. And related to this, I've added this extra bullet. that we've had problems just taking UVM test benches that have been developed in different sites in different parts of the world, because someone's developed their block-level test bench and maybe they've influenced their scoreboard from their stimulus, and now that doesn't integrate within the full system. So it's not just legacy test benches. And the biggest problem we've had really is with developing scoreboards and self-checking test benches. I think Mark was talking about automating the stimulus, but actually sometimes the major work is actually in developing the reference models to make the test benches self-checking. Right, the last, how am I doing for time? Okay. The last official challenge, I added a fourth one, that was related to the unique selling point is people will say, well, we can just run this on the hardware. You know, why spend lots of time, you know, developing these complicated test benches when we can just run it? And that's not a bad thing. If you're developing an SoC and you go buy an emulator, that's considered prudence. And it was considered hacky if you did an FPGA design and you just tried it on the FPGA. So providing you do it in a structured manner, it's good sense. But there are some challenges with this. Firstly, you don't always have your hardware, or you may have prototyping boards or whatever. And then when you do find a problem, if you do, we've got FPGAs which are huge designs now, and even if you can stimulate the problem, trying to home in on it and then getting back into a simulator to actually work on it and find it is very, very difficult. You just don't have the same level of visibility. And okay, supposing everything's going fine, how do you know you've tested it? You know, in a simulator, you've got functional coverage, you've got code coverage. You don't know that just because you've, say, connected a spine and tested and run millions of packets through something, that you've actually hit some of the corner cases. So what would be really good is to have some unified methodology, and we're just hearing some suggestions about standards, so that we could integrate the hardware and simulation environments together. And the last one is, having put the three challenges together, something had come up, and those are things we've had to date. And in our discussions, we came up with partial reconfiguration. And this hasn't been a challenge yet, but the day after I wrote these slides, this was in some presentation that we went to about some future work, so this is going to become a problem. And partial reconfiguration is where you take an FPGA and designate part of it as a replaceable part of the design. Those that remember software overlays, it's a very similar concept. So this is different from a straightforward design, because you need to take something out and put it back in while something is running. So simulators, the whole environment doesn't really allow you to do this. It's a bit like power aware, but power aware, the thing's fixed, you're just switching it on and off. Here we're taking it out and putting something else in. So the challenge for EDA vendors really is, how do we use their tools to verify these kinds of designs? And lastly, I just listed a few things that we also considered in our meetings. Standard problems everyone else has. The level of skill required to develop these complicated object-oriented software systems. The fact that UVM is very complicated for beginners to use, but then you end up building complicated systems because it doesn't do everything. Parameterized IP and so on, but I listed them just to support those. There were many, as I said, were covered last year, so I'm sure we'll have some responses to these. And that's me done. Does anyone have any questions?
Thank you very much. Thank you very much, Heather. Any questions?